Hi, this presentation is to discuss about the machine learning project. Our project is Kaggle Leaf Classification Competition. This is the agenda of this presentation. First, we would like to start introducing ourselves and our roles in the project. After that, we would mention about our Kaggle rank and brief explanation of the problems. Next, we will talk about our data analysis and initial approach. Finally, we will finish with conclusions. Our team consisted of Andre, which is responsible for ensemble model, Fieni, which is responsible for numerical model, and Kevin, which is responsible for numerical and image model. Our group able to achieve first rank in this Kaggle competition with a score 0.0000. The problem statement is that, given 99 species leaf images, each species contains 10 training instances, we need to predict a test dataset. Each training instance contains an image and 192 numerical features. From our analysis, we are able to conclude several insights. The data is balanced. Each class contains 10 images. The image size varies, however, the aspect ratio for same species is similar. Some image is flipped horizontal/vertical. Some image is rotated, but only a small amount, 0 to 20 degrees. Numerical features given is already normalized between 0 to 1. Even though all the feature values range fairly between 0 and 1, we went ahead and normalized it once again, using standard scalar, whose function is as above, which will ensure every feature has mean of 0 and standard deviation of 1. For the image, we need to pre-process. First of all, as the image is grayscale, we believe it would be easier for the model to learn the features of the image if the image is binarized, which is 1 or 0. Because we notice that there is a gray color outside the leaf boundary, probably dust, that is not very visual to human eyes, but might make our classifier harder to extract the features. We also need to resize the image to 192 × 192, but we must make sure that the image is not stretched when resized, because there are some leaf that is the stretched version of other leaf species. We use a tf.dataset to generate an infinite number of data augmented image, using pipeline to rotate randomly, random flip. Here, we see 10 examples of the images that we run on the pipeline multiple times. We can see that same images appear in different rotation. We believe that using this data augmentation techniques, our model can be more generalized and not overfitting the trained dataset. One of our approach is to use random forest and KNN, because when we plot the numerical feature, we can see that same species actually in the same region. Next, we also want to see how random forest and decision tree differ. Finally, we try to use ANN. At first we didn't think that ANN can be used in this problem due to small dataset, however, it turns out that ANN performs the best among all approach. For image classification, it is common sense and very popular way to use CNN, but there are several ways like transfer learning or create our own CNN. In this case, we use our own CNN due to resource limitation. And since the image is quite simple and grayscale, we believe that it is not required to use transfer learning. Because most transfer learning problem is optimized for RGB image. This is the table of our result. Here, we can see that our ANN achieves the best leaderboard score. We suspect that our numerical and image model has low leaderboard score, despite high validation score due to image data obfuscate the numerical data. Hence, we think that we can use the numerical model only at first, and use the image later. As numerical is very fast to train, it will also save our time when we tune the model. Below is the design of our ANN. The design is achieved after many trial and error. The detail of the trial and error can be found on our report. To finally achieve the final model design, we changed several parameters to one by one in order to find the best parameter. So our some idea that we came up at first is, we will try to use only numerical data to predict. We will try to combine numerical and image to predict, and see if the result improved. Next, after many trial and error, we came up with a new solution to ensemble the numerical-only model and image-only model. And finally, we changed the prediction to 1 or 0 to maximize our result to 0.0000. This is the numerical-only model, as our initial submission, without using our final model design. From here we can see that the result is actually not so bad. Next, after several tuning, we can achieve 0.01234, however this is the best as we can get with only numerical. We did try quite a long time to keep tuning it, but this is the best result that we can get. It seems that it is not possible to achieve first place with only numerical data. Next, we try our next idea, which is to combine the numerical and image, and the best result we can get is 0.6090. We think that the image data may obfuscate the numerical prediction. Next we back to our numerical 0.01234 result, and we binarize it to see how well is our first choice prediction. Here, we see that the score went worse. And we also see that there are several species under same genus that only differ a bit. This may be easy to see using eyes, but it may be hard to represent it in the numerical feature. Hence, we can conclude, because our score increase when we change it to binary, we think that there are answers that our first choice prediction is not correct, but second or third place may be correct. So we think one possible solution is to find a threshold where if there are more than one prediction above this threshold, we should repredict it using second model. From second point, I believe that it is possible to train an independent image classifier to repredict the confusion row generated from above. In summary, we found that the best threshold for our model is 0.025. The threshold may be quite low, because we can see that in the slides that these two species is very different. However, it may be also because one of the numerical features given is the margin from the top of the image, which feature have high weight. So in summary, this is the complete pipeline of our predictor. So the full procedure for our final classifier is: first, we create a numerical classifier and find the threshold of confusion. Next, using the threshold, we can filter out the test data that has more than one data that has probability higher than threshold. After that, we create a confusion species graph from the data. The confusion species graph is to ensure that we don't have multiple overlapping classifier. And for each connected subgraph in the confusion graph, which we can say confusion species, as shown in previous slides, we train an image classifier. After that we predict each data using its suitable classifier. What we mean by suitable classifier is, as long as the confusion species of the data is subset of the classifier confusion species set, we can use that classifier. So finally, after several tuning and binarizing the result CSV, we are able to gain the perfect score on Kaggle. This is the end of our presentation. Thank you for your attention.